Now that we've learned how to calculate the molar mass, let's see if we can look at some applications of it. So once we are given the formula of something, we can easily use the molar mass to go back and forth between the mass of the substance and the number of moles present. So for example, let's say we wanted to ask ourselves a few questions here. So first, let's start off by finding the mass of a given number of moles of carbon dioxide. So switching over here to our notes sheet, we want to find the mass of 3.55 moles of carbon dioxide. And you'll notice that we already calculated the value for carbon dioxide there for the mass of an individual molecule. So therefore, we know that carbon dioxide is 44.01 grams per mole as the molar mass. So to convert from moles to grams, we simply use this conversion factor. Remember, when we say per, that just means for every one. So 44.01 grams of carbon dioxide is equivalent to 1 mole of carbon dioxide. So starting with 3.55 moles. And I do want to write the formula, even though I only have one compound here. We want to get in the habit of that because when we start getting into talking about reactions, there will be often two formulas within the same calculation, and we need to keep those straight. So to get rid of moles of carbon dioxide, down here this is moles of carbon dioxide. So every 1 mole of carbon dioxide contains 44.01 grams. And I'll just put carbon dioxide even though it's obvious at this point. Moles cancels. So putting this into the calculator, we have 3.55 times 44.01, which comes out to be 156 grams. 3 significant digits there. Of carbon dioxide. Let's do exactly the opposite. Let's go from the number of grams of a compound to moles using glucose. So we already saw in an earlier problem that 1 mole of glucose has a mass of 180.15 grams. So I'm just going to use that value in this problem here. So we have 985 grams of glucose. And we would like to convert that to moles. Now, when we do this, a lot of people have the immediate desire to use Avogadro's number. The only time we need to use Avogadro's number is when we are dealing specifically with numbers of atoms or molecules. And that's not coming into play here. We're just wanting to go to moles. So the only thing that we're going to need is the molar mass. So we want to get rid of grams. So I want to put grams down here of glucose. And I'd like to get moles of glucose up here. The unit I want. And we saw in that problem that there are 180.15 grams of glucose in a mole of glucose. And that's all that's required to do this problem. So putting that into our calculator, we have 985 divided by 180.15, and that gives us 5.47 moles. Of glucose. You do this calculation a lot in chemistry, so it's an important one to master. Let's go into a little bit different direction here. Let's say we want to find the grams of carbon in 50 grams of carbon dioxide. Well, there's actually a number of ways we could do this. So let's first start by going from grams of carbon dioxide to moles of carbon dioxide. So we know that there are 44.01 grams of carbon dioxide in a mole of carbon dioxide, which we have just established. Now, looking at the formula, what is this telling us? Well, for every carbon dioxide molecule, I've already drawn this a few times, I think, in the notes, every one of these has one carbon molecule, one carbon atom in it. Every 2 carbon dioxides have 2 carbons. Every 10 carbon dioxides have 10. So we could reinterpret this as just saying every 1 mole of carbon dioxide has 1 mole of carbon in it. We did something similar a little while ago. So we're just going to go ahead and add that so that we can get rid of all the parts except for the carbon. So 1 mole of carbon dioxide has 1 mole of carbon in it. So now what do we want to do? We want to find the grams of carbon. That's easy, because if we look on the periodic table, a mole of carbon has a mass of 12.01 grams. So you see, we're just using the same techniques that we used in unit conversions here to go from one set of units to another. So every mole of carbon has 12.01 grams of carbon in it. I'm going to go ahead and erase some of this because it's cluttering up my space. And let's go ahead and solve this. And again, moles of carbon cancel. As you're going through this, just make sure that all of these make sense. 50.0 grams is what you're given. 44.01 grams of carbon dioxide is equivalent to a mole. We've already established that. Every mole of carbon dioxide contains 1 mole of carbon. Every 1 mole of carbon has a mass of 12.01 grams. So all of those statements are true. So we have here 50 divided by 44.01, since that's in the denominator, times 12.01, since that's in the numerator, and we don't need to pay any attention to any of the ones in between there. And this would give me 13.6 after accounting for significant digits. So 13.6 grams of carbon. As I mentioned, there's other ways we could have solved this problem. I can think of at least 3 ways total. But this is probably the most direct way using the methods that we have learned so far. Now, let's take what we've just learned with chemical equations in the beginning of this chapter and start combining this with information about the mole and molar masses. So, the coefficients that we got when we balanced equations can be interpreted as telling us the ratio of the moles of reactants to each other, as well as the ratio to the moles of products. So when I look at this equation, I'm first tempted to read this as saying, well, every 4 iron atoms reacts with 3 oxygen molecules to make 2 iron 3 oxide units. Remember, ionic compounds don't make molecules, so we'll just call that a unit there. But that kind of an interpretation is very messy. We're not really going to be dealing with anything on an atom-by-atom basis. Everything we're going to be measuring in the lab will be in grams or milligrams or liters or milliliters. And so working at the atomic level doesn't really make sense. Instead, we're going to interpret these as moles. So this is saying simply that every 4 moles of iron reacts with 3 moles of oxygen to produce 2 moles of iron 3 oxide. And that again is a ratio. We don't have to have 4 moles. We could have 1/10 of all this. So this could be 0.4 moles plus 0.3 moles gives you 0.2 moles. So this is just a ratio, just like any recipe that we are cooking with. So we can then come up with these different ways of relating these together. So for every 4 moles of iron, I need 3 moles of oxygen. Or for every 4 moles of iron, I can produce 2 moles of iron 3 oxide. And we will construct conversion factors from these right here. So we're going to use dimensional analysis just like I've been using all along here for all of these different unit conversions. And we set the ratios up by simply taking the numbers from the balanced equation and putting them in front of moles of that given chemical. So using the balanced equation that we just saw on the last page, we said that 4 moles of iron will make 2 moles of iron 3 oxide. Notice I'm always reading from the denominator first because we know that this is the unit that will cancel, the unit in the denominator. What other ratios can we get out of this? Well, we can get the reciprocal. For every 2 moles of iron 3 oxide, I need 4 moles of iron. I could use the relationships between iron and oxygen. So if you remember, on the balanced equation that we saw just a moment ago, there was a 3 in front of oxygen. So every 4 moles of iron reacts with 3 moles of oxygen up here. So there's ultimately a total of 6 different conversion factors that I could construct from that equation. So let's start with the easiest possible use of these chemical equations. So what we have here is a balanced equation giving us the amounts of hydrogen which reacts with oxygen to make water. Notice that I've chosen to include the states here. That's not always a requirement, and usually we only include the states if that information is useful, but I just wanted you to see it in use. So let's read this equation in a useful way involving moles. So to produce 2 moles of water, we need to combine, according to the equation, 2 moles of hydrogen with 1 mole of oxygen. That's just these numbers right here. Put a 1 there if I want. How many moles of each reactant are required to produce 10 moles of water? Let's go ahead and go over to our notes to take a look at that. Okay, so back to our notes page here. We already decided that 2 moles of water needs 2 moles of hydrogen to be combined with 1 mole of oxygen. So that lets me come up with a lot of different conversion factors. 2 moles of water to 2 moles of hydrogen, 2 moles of water to 1 mole of oxygen, and the inverses of both of those, or rather the reciprocals, and 2 moles of hydrogen to 1 mole of oxygen. So first question, how many moles of each reactant are required to produce 10 moles of water? So each reactant means I need 2 answers here. I need 1 for hydrogen, and I need 1 for oxygen. I can tell you in advance that the answer for hydrogen is going to simply be 10. And the reason for that is whenever we have the same number in a chemical equation, it's always going to come out the same. A 2-to-2 ratio is the same as 1-to-1. Let's prove that. So we want to know how much hydrogen will make 10 moles of water. I want to put moles of water in the denominator. And moles of hydrogen in the numerator. And now I just use my ratios from the equation. There is a 2 in front of water and a 2 in front of hydrogen. So every 2 moles of water needs 2 moles of hydrogen. And of course, these just cancel out. Incidentally, those are always treated as exact numbers. And so the only thing we're left with is 10. So we have 10, and the units that are left over are moles of hydrogen, just like was predicted. How about oxygen? Well, I can already tell you that the answer is going to be 5 because this is a 2-to-1 ratio. So that means I always need half as much oxygen as hydrogen. But let's, again, prove this. Now, an important concept here is I could start now with 10 moles of hydrogen or 10 moles of water. You only need to know the amount of one chemical to find the amounts of any other chemical. So either of those would be fine starting points. I'm going to use the 10 moles of water just like I did here. And now the ratio is going to be a little different. So we want to get rid of moles of water. And we would like to have moles of oxygen. So just reading the numbers from the balanced equation, a 2 goes in front of the water, and a 1 goes in front of the oxygen. So we have 10 times 1 divided by 2 is just 5, and there's only one significant digit here. So this should make sense to us. If we were to write these numbers up above the equations, it would be exactly the same ratio. Every 10 hydrogens reacts with 5 oxygens to produce 10 waters. However, we've agreed that when we balance equations, we want to always divide by the greatest common divisor, which would be 5 here. So dividing each of these numbers by 5 would give me the same balanced equation. We don't need that there, so let me go ahead and get rid of it. How many moles of water can be produced at most from 13 moles of hydrogen? And how many moles of oxygen would I need to accomplish this? So, similar problem here, except now I'm starting with a reactant and I want to figure out how much product. So the first part, I have 13 moles of hydrogen. I would like to get that to moles of water. So we want to put moles of hydrogen here, and moles of water in the numerator. And again, we just use the numbers from the balanced equation, which we saw were 2's in front of both of those chemicals. So moles of hydrogen cancels. 2 over 2, of course, is just 1. So this leaves me with 13 moles of water. Shouldn't be surprising. How much oxygen do I need to get that to work out? Well, as I mentioned in the previous part, I could start with either of these numbers. Once I have one of them, I can use either to continue on here. So again, like last time, I'm just going to use what I started with here. So let's say again that I have 13 moles of hydrogen. And I want to convert that to moles of oxygen. So the unit I want to get rid of is moles of hydrogen. And the unit I would like is moles of oxygen. And going back to my chemical equation, in case we forgot, we had a 2 in front of the hydrogen and a 1 in front of the oxygen. So we can just fill those numbers in. So we have 13 times 1 divided by 2. This would be 6.5 moles of oxygen. So, or 13 halves. I cancel out my unit there, moles of hydrogen and moles of hydrogen, so I know that I get moles of oxygen. Okay, let's go ahead and continue on to the next problem. So here you're given another chemical equation, but this time you are told that the equation needs to be balanced. So that's the first thing we're going to need to do, because we can't relate moles to moles without balancing the equation. And then we're going to answer A and B. Okay, my first temptation here would be to say, well, let's balance hydroxide. The problem, though, is there is no hydroxide on this side, so I'm going to have to do this atom by atom. My temptation is going to be to start then with chlorine. If I see 2 chlorines here, that's going to be easy to fix by putting a 2 here. What else do we need? Well, if I've got 2 hydrogens plus 2 hydroxides, that's 4 hydrogens, right? So 2 times 1 plus 2 times 1 is 4. So this would be 2 times 2. We need a 2 right there. What about oxygen? Well, that fixes oxygen too. So we have 2 times 1 oxygen, 2 times 1 oxygen. So we are balanced here. And let's just read this in words for practice. This is hydrogen chloride, or as we'll see soon, it'll be called hydrochloric acid, plus barium hydroxide makes water and barium chloride. So still staying with just moles here, how many moles of each reactant do I need to make 5.75 moles of water? So I want to know how much hydrochloric acid and how much barium hydroxide I need to get this much water. I can already say that the amount of hydrochloric acid is going to be the same as the amount of water because they both have the same coefficient in front of them. They're 2 to 2 or a 1 to 1 ratio. But let's just show that. So we have 2, So let's start that again. 3, 2, 1. So we have 5.75 moles of water. And the equation says that every 2 moles of water needs 2 moles of hydrochloric acid. So moles of water cancels. And I have 2 over 2, so those of course cancel, leaving me with only the starting number, 5.75. And the unit, which is left over, after all the canceling, is moles of hydrochloric acid. Now similarly, I know that for the other reactant, I'm going to need half as much. This is a 2 to 1 ratio. So 5.75 moles of HCl or water. Again, it doesn't matter. You just need the amount of any one chemical to find any of the others. You could pick either one. I'm going to still stay with water. So we know that every 2 moles of water needs 1 mole of barium hydroxide. So putting that into the calculator, actually it's not too hard, we should be able to do that one in our head, but that's going to be 2.875. But we have to adjust that down to 3 significant digits. As I mentioned before, all of the numbers that are in the balanced equations are considered to be exact numbers. So here we have, again, 2.875, which rounds to 2.88 if we need 3 significant digits. So I could put this as a sentence here. 5.75 moles of hydrochloric acid reacts with 2.88 moles of barium hydroxide, and that gives me 5.75 moles of water. Let's stick with this equation just a little bit longer and go into part B. So what is the maximum number of moles of water? So that's what we're going to want. Moles of water I can get using 18 moles of hydrochloric acid. Again, that should be easy because they have the same coefficient. 2 is in front of hydrochloric acid and 2 is in front of water, so you'll see that I'll get exactly the same answer. So if I have 18 moles of hydrochloric acid, let me be clear, when I say the same answer, I mean the same number of moles. So 18 moles of hydrochloric acid, according to the equation, for every 2 moles of hydrochloric acid, I will make 2 moles of water. The moles of hydrochloric acid cancel. The 2's cancel. And this leaves me with just 18.0 moles of water. So if everything is perfect, that's what I would expect to get, 18 moles of water. How much barium hydroxide would I need? Again, I know that it's going to be half as much according to the balanced equation, but let's just show that. So if I have 18 moles of hydrochloric acid, according to the balanced equation, every 2 moles of hydrochloric acid needs 1 mole of barium hydroxide. And so I have 18 divided by 2 is 9, and I need 3 significant digits, so that would be 9.00 to get 3 significant digits, moles of barium hydroxide. And I'm going to go ahead and stop here, and I will finish this topic off in the next video. Thank you.